Good afternoon, everyone, and welcome to today's webinar titled Oil Analysis Limitations. My name is Taylor Colon, and I am the Customer Engagement Specialist here at Test Oil. I will be your host for today. Before we get started, there are a few things I wanted to go over. First, everyone is muted. We are recording today's presentation, and by being on mute, this will ensure high-quality recording. Second, please feel free to use the questions box in the GoToWebinar application. We would be happy to answer any questions that you may have. Finally, the webinar recording will be distributed later today along with a survey. Look for that in the email you registered with. Let's get started. Today's webinar is presented by Evan Zabowski. Evan is a certified lubrication specialist and a senior technical advisor here at Test Oil. All right, and Evan, if you're ready, I'll pass the controls over.
Great, thank you, Taylor. So as he said, today's presentation is entitled Oil Analysis Limitations, but I tried to think if I could call it something else, what would I call it? And my alternate title is Things You'll Never See on a Report, at least not in the same way. When we talk about oil analysis, we always discuss how to interpret the results. What do they mean? What are we going to do next? And the big point of this particular presentation isn't really to get into what they could mean, but rather what they probably don't mean, or what you think you're going to see but aren't going to see. So the very, very first thing we should talk about is test selection, because that essentially is the major limitation to an oil analysis report. Now, once I get through that, I'll talk about the limitations of some specific tests, but understand that oil analysis is only going to answer the questions that you pose by selecting the test that's going to give you the right data. So when we look at test selection, commonly speaking, we categorize oil analysis into about three different facets. There are the physical and chemical properties, there's contaminants of some kind, and there's generally wear debris or wear mechanisms that are measured through some technology. So the goal of my presentation today is to take a few of these common and seemingly similarly categorized oil analysis tests and identify what the limitations are between them, so you can understand why sometimes you don't get the results you're perhaps looking for, or maybe this will help clarify how you've been misinterpreting what that data is showing you. So this is the grouping that I chose. Basically, I'm going to take a look first at elemental spectrometry and compare it with particle counting. Then I'll get into the fluid properties and take a look at acid number, MPC, RPVOT, ruler, and I'll very briefly throw in ultracentrifuge. But the presentation will wrap up with a quick look at ferrous wear concentration as it relates to analytical ferrography, but then tie it right back into elemental spectrometry and particle counting that we are going to begin with. So to get started, let's talk about elemental spectrometry. Now, I've mentioned this in other webinars, so bear with me if you've been listening to the whole series, but the basic principle of elemental spectrometry is to take a sample, dilute it, inject it as an aerosol into a plasma, and in the plasma it will become an ionized aerosol. So what happens is essentially it's going to give off a bunch of light. Now we analyze the wavelength of light and the intensity of the light at that wavelength, and it tells us how much of each element is there. But this is the key thing, it is an elemental concentration. So understand as a limitation to this test, it is not telling us what kind of alloys, compounds, chemicals, or anything like that is present in the sample. It is telling us about the elements that make up the various components from within the oil. And just as a quick visual, if you take a look at aluminum, tin, and lead, which to the naked eye all appear like silver-colored metals, this instrument is capable of discerning one from the next to the next. But picking on tin and lead as an example, tin and lead could come from Babbitt. But this machine doesn't tell me I've got Babbitt. It just says I've got X amount of tin and Y amount of lead, and I have to intuit from that if that in fact means Babbitt. But brass and bronze also contain tin and lead, which would as well have copper in it. So sometimes you can use an additional metal to maybe narrow down your choices. But still saying that, you don't definitively know. It is an elemental concentration only, That's the first limitation. Another limitation that's not as widely understood is the particle size limitation. Because we are diluting the sample and introducing it as an aerosol, you have to appreciate, for one, this instrument is not going to be given any large particles. So if you can see them with the naked eye, they don't actually make it all the way through the instrument to the point of measurement. But what is measured within that aerosol are particles generally within the 0 to 5 micron range. Somewhere around 5 microns, it's widely understood that the accuracy begins to drop off significantly, and depending on the literature you read, it cuts off at around 8 to 12 microns, so I'll just use 10 as a nice round number. But basically 0 to 5 is measured accurately, 5 to 10 accuracy declines, and above 10 you can kind of consider all bets are off. It's not that the instrument doesn't see the particles, it's just it doesn't measure them accurately, and that's why I say it's essentially blind. So the second limitation, after it's an elemental concentration only, is it only measures the really small stuff. And this is just a quick graphic from Spectro showing what the accuracy looks like in terms of elemental spectrometry, but thankfully there is a bit of a handshake here to other large particle tests. So in a nutshell, it is measuring only the elements, not compounds, alloys, or chemicals, as I said, and only measuring the really small stuff. Now, what this means to us is that we can expect that if it's wear from normal wear mechanisms, or if it's expected airborne contamination, this test will probably indicate those levels. However, if it's wear from severe wear modes, so considered abnormal, or abnormal airborne contamination, this test may not measure them. So we have to go into elemental spectrometry expecting to know these two particular limitations, that it is not telling us, like I said, a particular alloy. It doesn't say you've got Babbitt, but also if it happened to be some pretty significant severe wear occurring, this instrument might not see those particulates simply because they're too large to be introduced into the plasma, or they may not ionize completely within that plasma. So keeping these couple thoughts in mind, now let's talk about particle counting, and I'll tie the two together. Now with particle counting, there are two methods to particle counting. So one method, very popular, is called optical particle counting. And with this method, what we're doing is we're taking a thin film of sample and flowing it through a cell, so it's a moving sample, and we're shining essentially a very bright light through it. Now this bright light is aimed at a photodetector, a CCD sensor, if you will, similar to a digital camera. But here's where the key limitation kicks in. How it measures a particle is by a shadow. Now, many people are familiar with the fact that this form of optical particle counting, which is sometimes referred to as light blockage, is counting shadows, but the aspect of the shadow that they don't recognize is how it sizes the shadow. The way the instrument sizes the shadow is by calculating the area of the shadow. And then what it does is what we call spherical equivalency. So it takes the area of the shadow and says, well, what if that shadow was created by a perfect sphere? Now, as you can hopefully appreciate, a perfect sphere would create a circular shadow. So it's essentially giving us the diameter of a circle that would occupy the same amount of area. So the key limitation to this test is it is not telling us the longest dimension of the particle, it's not telling us the shortest dimension of the particle, and it's not even telling us the average dimension of the particle. It is doing a spherical equivalency. It is assuming, and this is a major assumption, that the shadow that it sees has been created by a perfect sphere. Now, further to this, remember that it's only a particle count. So it's just counting how many of these that it sees. It's not identifying, again, if they're metal, if they're soot, if they're dust, if they're dirt, if there's some other type of material. It just says it is something that created a shadow. So on the interferences side, understand that with this particular method, there are other things that may cast shadows as they flow past the light source, and air bubbles, water molecules, and even soft varnish-like particles fall into that category. So to mitigate the measurement of these, you would have to actually dilute your sample with a solvent. So what I'm saying is if you measure your samples neat, chances are you're going to err quite high in comparison to a laboratory prepared sample. But going back to the limitations just for a quick second, The instrument, as it is set up, has about a 100 micron gap. So that's the essentially width of the cell that the oil is flowing through. So particles much larger than, say, somewhere around 200 microns just simply don't even enter into the cell. So that's why we set an upper limit of around 100 to 200 microns, as no particles larger than that are included in the count. But the other side of that is that we don't count or classify any of the particles smaller than about 4 microns. So right away, hopefully this is triggering something in your mind going, wait a minute, if elemental spectrometry is 0 to 5 microns, and this is essentially 4 and up, that's not a lot of overlap. So therefore, we should already have in our minds an idea that this test and elemental spectrometry will not correlate very well with each other. But let me continue on with the other particle counting method. The other way we could measure particle counting is called pore block. Now, pore block is when you push an oil through a calibrated screen at a constant pressure, but you measure how fast the flow decays. So sometimes this is referred to as a flow decay measurement. But either way, what we're doing is we're pushing an oil sample through a screen, and it's got a bunch of similar sized holes. Now, these holes obviously don't plug up with particles smaller than the holes at first. They have to plug up with particles larger than the holes. Now, as some of the holes get filled up or blocked, now the screen is able to trap smaller and smaller particles. So what this instrument does is it plots the flow decay, and it is therefore able to use its own algorithm for telling us what size particles we have within the fluid. But in doing so, it is an extrapolated distribution. All the pores in the screen are only one size. So essentially, we're really only measuring one size of particle. And from there, we're making a very broad assumption as to what the other particles in the sample would look like. So we're assuming a linear distribution, which may not actually be the case, remembering that most particle counting is reported as 4, 6, and 14 microns. What if you're filtering at 10 microns? If you're filtering at 10 microns, it could be appreciated that you're not really touching a whole heck of a lot of the 4 to 6 micron particles, but you should be taking out a reasonable number of the 14 or greater particles. But with this instrument, it assumes a linear distribution. So depending on how that screen has plugged up, this method can be fooled into thinking there are actually far fewer particles overall than maybe your filtration was capable of. But it could also skew on the high side too. So as you can see, neither particle counting method really gets into a great deal of accurate measurements. So in a nutshell here, remember, they're counts. That's why they're called particle counts. So they don't identify the what, but neither method is really measuring the actual size, nor is it doing it in a very intuitive way. Many of us could deal with the results if we knew that it was always the smallest dimension or always the largest or just an average. And we know the particles aren't shaped like perfect circles, squares, or rectangles. But it is hard to interpret a particle count, which is why it's so important to just look at the overall trend and not really get too detailed about what particles we're seeing. Now, like I said, do expect optical particle counting to trend high because it may be counting other things that are creating shadows. But also expect pore blocking to miss any nonlinear distributions, like I said, due to filtration or something similar like that. So where are we then? Well, kind of summarizing what I've talked about so far anyways, is that we know that elemental spectrometry and particle counting aren't measuring the same particle sizes. So in saying that, we shouldn't expect that they will always correlate with each other, but we can work with that correlation. If both are high, that indicates one thing. If both are low, that may indicate something else. When only one is high and the other one is low, we have yet a different idea. So my basic summary as I interpret data is this. If I have high elemental spectrometry, but low particle count, I'm assuming most of what I'm seeing is from normal wear modes, normal contamination. As both begin to increase, I start to think I'm transitioning from normal to severe or abnormal. And if my elemental spectrometry is low, but the particle count is high, then I will assume then most of what I'm seeing is from abnormal wear modes and or contamination. So I kind of look at it like a teeter-totter that way and just say, well, what if one's high and the other's low, or vice versa? Where am I? How do I interpret that? So as I said, the correlation or lack of correlation can be telling still. And leaving it at that, I will move on to the next round of testing. So in fluid properties, we talked about you're measuring physical and chemical properties. So let's understand what we're actually measuring here. So I'll begin with acid number. Now, acid number can be measured, again, two different ways, and they're incredibly similar, but they actually still have a significant difference. So one way we have of measuring acid number is called colorimetric. Now, colorimetric is when we do a titration and we're knowing if the titration is complete by a color change. So the color change that we're going for is a bright orange color to a dark greenish brown, which you can see in the picture there. So an acid number test is meant to measure the acidic constituents in an oil. And as soon as you say that, a lot of people go, what's an acidic constituent? Well, a constituent can mean anything. So any form of acid that may be present in the oil. Now, this is not always a degradation byproduct. This may in fact be from the additive chemistry. It's also worth noting that acid number doesn't measure all acids, but I'm going to get to that in a second. It does only measure the stronger acids. So the limitation to the colorimetric method is that, generally speaking, acid number is a very slow to react parameter when we start dealing with large volume applications. And by large volume, I mean, say 4 drums, 200 gallons or larger. We tend to dilute the results quite a bit, and we have to rely on some of the other testing that I'll follow up with in a second. Now, as an interference to this test, because like I said, we're looking for a dark greenish brown color as a color change, if the oil sample itself is dark to begin with, it can be difficult to even see this color change, and therefore you might not report an accurate result. It's also worth noting that ASTM points out high water content may skew the results from this test. And this is because water causes acids to dissociate. So we can have weak acids dissociating into stronger acids. So what that means is we could have acids that normally would not be measured by this test becoming strong enough that they can be measured by this test. So in short, you kind of chase the answer, and that the slower you do the titration, actually the higher the result you might get. So you have to appreciate that sometimes you can skew your own results just because of some outside mitigating factor like water content. Now, the other way of measuring acid number is what we call potentiometric. Now, potentiometric uses all the same chemicals at all the same volumes and concentrations as the colorimetric, except it does not have a color indicator. What instead it uses to determine if the test is over is essentially a conductivity meter. So it measures the potential across a gap, and it plots this potential over time. As we add the titrant, we typically look for the inflection point as a way of identifying where in the curve can we expect to find that the sample has been neutralized. Now, with this particular variation, the limitations and interferences remain the same, except it does not have the darkness factor. This version of the test can be performed on very dark samples. Now, I've described the two methods, and I made mention of the differences just briefly. Why I mention this, though, is because ASTM has a very definitive statement within each standard for these tests, identifying that neither method can be compared to the other, that they do yield different results and can be substantially different results. Just as a quick example, I was dealing with a gear oil sample that was a new oil, wasn't even an in-service product yet. And through one method, we would get an acid number of about 0.5, and through the other method, we got an acid number of about 3.0. So a 6-fold difference in the results. So when I say they don't correlate, there is a potential that they could not even remotely look like each other. I'm not talking about just a small difference. Now, one of the other things I'd like to point out, and it's just a little bit of a pet peeve of mine, but it's kind of that useless trivia that does help remember an important factor about this test and further explain why sometimes we see what we see when it comes to certain results. Let me give you a quick little side story. Now, if you can read that text at the top, then you're pretty good at reading through the Gothic font, but it does say Ye Olde Tan Test. And why I show that font to you is just to give you a quick explanation of the history of English and printing. And you're going to see how this all actually relates to a very important factor of this test. Now, back when we had what we called Old English, which was, as you can see, the 6th to the 10th century, we had other letters in our alphabet, and the TH sound was represented by a letter called a thorn. And you can see it kind of looks like a weird P. Now, once we started moving towards Middle English, we replaced the thorn. We got rid of the thorn as a letter in the alphabet and just started using TH. But right around the time that we were doing this, that's when the printing press sort of came to England. But early printing presses didn't have English typeface. They had German and Italian typeface, which German and Italian language does not have the thorn. So they chose to use a Y because they look quite similar. So I'll give you an example there in the text. So when the very first King James Bible was printed, a lot of thorns were replaced with Ys, and that's why we tend to read things and say ye olde this, when in fact it was never pronounced with a Y. It's just a workaround that we had with early printing presses. So pretty much what I'm saying to you is this: if you've ever used the word ye to replace the word the, you've been in error. But I'm not here to point out errors. I'm here to explain something. So what I'm explaining to you is it was never right. Well, the other thing that was never right is the name tan. Total acid number, as you may know this particular test, was actually its official name, but it was not correct. It doesn't actually measure all acids. It only measures stronger acids, not weak acids. So the name tan was never correct. But much like how ye has propagated over all the years, and we continue to use it to this day, even though it was never correct, people still can continue referring to this test as tan, and that's where my pet peeve kicks in. The learning point, though, out of this is to understand why it doesn't measure all acids. So it doesn't measure the really weak acids. So there are some things in oils that are what we would call a weak acid rather than a strong acid. So when we measure acid number, we're actually only measuring the strong acids. So we're not seeing truly everything in the oil sample. That's a key thing to note here. But just to finish my little story here, just to give you some useless trivia for the day, sticking with our ye olde tan test here, I can give you another slightly more modern example of, again, how English language has shifted, and so how it can explain some of the things we still see to this day. But I give you the more modern example of the letter U and V. Now, in the Latin alphabet, they didn't have two separate letters for those. They used the same letter for both. So whether it was a consonant or a vowel, they would use it, which is why you sometimes see those old buildings and they look like they've got a spelling mistake or something like that. It's because at the time that was correct. And now you know why we call that particular letter a double U, not a double V, because it was always a U. We just had two different uses for the U. So I know I digress, but just interesting trivia for the day. So getting back to our acid number discussion, remember, neither method correlates with the other, and we're not measuring everything. We're measuring acidic constituents that are of a stronger nature. Some of these may be additives. And because we're measuring only strong acids, the weak acids are not being measured, but may become strong acids later. So sometimes you'll get a spike in water content, and that could give you a significant boost to your acid number. And you'll think, well, this is off trend, this doesn't match, and you think something else is going on. But that is the limitation to the test. It only measures the strong acids, so you could have a significant amount of weak acids sitting, more or less dormant, waiting for the opportunity to dissociate into stronger acids. So understanding some little limitations to acid number, and like I said, also learning some useless trivia about the English language, we can appreciate that acid number is not called total acid number because it's not measuring all acids, but also of the acids that it's measuring, not all of those ones are actually degradation byproducts indicating a problem. Now, continuing on here, let me explain a few more tests. RPVOT It is an accelerated kill test. We take an oil sample and we force it to oxidize. So what we do is we give it water, copper, and a pure oxygen environment. Now, those three things form basically an oxidation triangle. The copper really wants to oxidize by reacting with the oxygen. The water is going to act as a bit of a catalyst or an accelerant. And to make sure it occurs in a brief period of time, we're going to stick it in a nice hot bath. Now, to ensure the oxidation does not take place, we have our oil in this particular contraption. So we rotate it at a slow 100 RPM to keep the oil splashing over top of the copper, and it's going to try and protect the copper. Now, how we know the reaction is going on is we measure the pressure. So when we first stick this apparatus into the bath, it actually pressurizes, because when you heat up any gas, it's going to try and expand, but we've of course sealed it so it can't expand. It increases in pressure. So once the pressure stabilizes, we sort of set that as a baseline, and then we measure it and we wait for the pressure to drop. The pressure will drop when the oxygen is reacted. So once the oxygen begins reacting with the copper and starts forming copper oxide, the oxygen is consumed. Because it's consumed, it occupies less space, therefore the pressure decreases. So the long and the short of it is, we stick the sample in the bath and we wait for the pressure to drop. How fast, how long it takes for that pressure to drop gives us a result in minutes. Now, the limitations to this particular test is we can only measure fluids that actually have an antioxidant, something that's meant to protect metals like copper, but it doesn't have any real significant interferences. So it's a pretty good test in many ways, but we have to understand a couple things here. You're supposed to trend the results. The single result on its own offers next to no indication as to how well that oil will perform once you put it into service. To give you a quick example here, you may find an oil that has a very, relatively speaking, low new oil value of 600 minutes could actually drop to 300 minutes as soon as you put the oil in service, which looks scary when you first see it. But then as the oil continues to be in service, it will drop by only a few minutes every month. So as you trend it over time, you'll notice small decreases. You may choose a different oil, on the other hand, that could have a new oil value of a couple thousand, 3,000 minutes, and they will drop at a much higher rate every month. So in the end, you may find that the oil that you looked at that had a, say, 600-minute new oil value actually outlasts an oil with a 3,000-minute new oil value. So it's very possible that you can have what would seem like conflicting data. So that's why you're always supposed to trend it and not supposed to just look at a singular value. The other consideration to this test is that even though you're measuring sort of how fast it's degrading, how much protection it's offering, sort of that indirect way of looking at things, you have no idea if during this test there's any acids or insolubles, i.e. varnish, forming. So while your RPVOT may decrease, you don't know if it has any other detrimental effects. You can assume, but sometimes you'll come out wrong. Now, speaking of the insolubles, the way we go about measuring those is with what we call MPC testing. Now, with MPC testing, it's a fairly straightforward test where you do a patch on it. So you pull some oil through a membrane patch. It's a very fine pore size. And then you analyze the color with a spectrophotometer. Now, if you're wondering what a spectrophotometer is, it's the same type of instrument we use in hardware stores to color match paint. So it's a very accurate way of measuring color on a flat surface. Well, what we do when we measure that color is we don't report it on the RGB or CMYK scales that you might be familiar with when it comes to digital video or printing. We report it on the LAB scale, which you see pictured there. Now, one of the values that we concentrate on is the L scale. It's the darkness scale. So we want to know essentially how dark the patch is, and the A or the B scale just gives us an idea what color it is, which helps determine what mechanism is causing the insolubles that we're trapping on that patch. Now, limitation to this test, understand it's only measuring what is on the patch. So to get on the patch, it had to be able to be filtered out of the oil, and also, as I like to kind of joke here, it had to make it into the sample bottle. So if you've got varnish that's already plating out all over the components within your system, obviously they're not in the sample bottle because they're plated out on your equipment. therefore we're not getting an idea of existing deposits. Now, as for interferences, it's worth noting that this test, because we're measuring darkness on a patch, anything else that might cause the patch to become dark could skew the results. So carbon is a pretty good example of something dark. Carbon can be produced through electrostatic spark discharge or microdieseling, so that could explain sometimes why you see a patch that looks particularly dark to the naked eye, or might even skew a little bit on the actual readout. So in a nutshell, remember, this test is only measuring the insolubles that made it to the patch, and to make it to the patch they had to be in the bottle, so it gives no indication of what's already plated out or deposited. Now, again, the idea with this, much like RPVOT, is that you're supposed to trend it from new. When you trend it from new, you can watch, in the case of RPVOT, the values will go down. In the case of MPC, the values will go up. Now, any increase that ends up plateauing may indicate that we are now depositing the materials, and any sudden decrease when no corrective action has been taken generally also indicates a sudden plating out of these insolubles. So we can intuit a little bit of what's going on here, but again, we're not necessarily measuring truly how much has deposited or formed on any of the surfaces. Now, the other way of doing this particular type of measurement is called ultracentrifuge. Now, with ultracentrifuge, you just take a sample of oil, place it in a test tube, you spin it at a ridiculously high RPM for half an hour, and at the conclusion of the test, you compare the bottom of the test tube with the visual scale that you see here. Now, the top half of the scale, 1 through 4, is generally considered okay. The bottom half of the scale, 5 and higher, is generally considered not okay. So it's a very quick and dirty kind of way of doing it. It's not necessarily as complete as a patch test, because it's not based on any sort of pore size. It's just based on density. So other things that may be present in the oil, like say water content, could pull down to the bottom of the test tube and alter how that particular little dot works. But again, I sort of reiterate the exact same limitations here, that you have no idea from that test how much is already deposited within the system. But as for interferences, beyond that, other things may form at the bottom of the test tube, like I said, like water. Do understand that because we're spinning this at such a high speed, we may actually impart energy into the sample, and it may heat up. When it heats up, it helps hold the varnish in solution, and we may not see all of it hit the bottom of the test tube. So to compensate for this, you can try chilling the sample, but if you over chill it, then you may force more things to condense or agglomerate and again skew the test tube. So there are a few things causing the results to be less than accurate. Now with UC, understand that it's only measuring the stuff that gets pulled to the bottom of the test tube, and it just has to be not soluble. So it could be varnish, could be any of those precursors, but could be particulate. Could be water. And much like the other test, like I said, doesn't give any indication of existing deposits. So I kind of treat this one as a lot more of a qualitative test than a quantitative test. But what makes it so nice is it's a lot easier for an end user to have some sort of intuitive interpretation of it than an MPC. An MPC, when you look at the patch, you can look at a patch that seems like it appears very dark to the naked eye, and you wonder why it doesn't have a higher result than another patch, which may look in fact lighter, but again, under the LAB scale, we can get much different results than what we think of with the naked eye. So this test sort of aligns with visual expectations a bit more than MPC, but I don't feel that it's really necessarily encapsulating as much information as the MPC is doing. Now, just continuing on one more time here with yet another test, the ruler. The ruler is a measure of the level of antioxidant additives in the sample. And how it does this is essentially we have to take the sample, dilute it with an electrolytic solution. So if you're thinking Gatorade, you're not terribly far off here. And then we apply voltage to the resulting mixture. Now, when we apply the voltage, we plot the voltage over time, and it creates those little cute graphs that you see off to the right there. Essentially, a new oil will produce the highest peak, so think like that dark blue line, and then every subsequent used oil will produce a peak that is slightly lower, lower, lower. So what we do is we measure the height and area of the peak as it compares back to the new oil sample, and we can tell you how much of your antioxidant additive is present compared to the new oil value. So it starts off at 100% and slowly works its way towards 0%. Now the limitation to this test is you actually have to have that new oil reference. Without that, there's no way of doing this test accurately. Also, much like some of the other tests, a single result does not really give you a strong indication of future performance. It is meant to be trended. You're trying to see what and this is what ruler stands for, the remaining useful life. So with this test, also understand that if you have any top-ups with alternate fluids, or if you're starting with a mixture because maybe you've switched suppliers or your supplier has switched formulation, that will skew the results and maybe cause you to not have even a remotely accurate result. And that's where I give you the example there, just two completely different oils showing you how vastly different the peaks are, even with similar additive technology. So in a nutshell for ruler here, remember, these are supposed to be trended. Just because you get what looks like low result doesn't mean things are looking bad. You have to see how fast how fast it took to get there and how fast you're declining from that point. Much like RPVOT though, as the result declines, there's no way of knowing if you're forming any acids or any insolubles. So how I basically look at this is as such. All these tests that I just went through are measuring some form of oxidation. That's the key thing. We're trying to measure degradation of the oil and its additives. But I think if you try and look at it from this perspective, it starts to make a lot more sense. Because RPVOT is actually putting the oil through its paces, now granted it's accelerated, and like I said, it's actually trying to kill the oil, it's a performance-based test. Ruler, on the other hand, as I just described, is measuring a true level of additives, so it's measuring a property. But acid number is measuring acidic constituents, and those may be an outcome, right? They could be degradation byproducts, but there are some that are part of the additive technology. So it's kind of measuring both a property and an outcome. But MPC and UC in particular are measuring the outcome. They're measuring the insolubles that have formed as a degradation byproduct. So if you look at those particular sort of comparisons, you can appreciate why, even though we're essentially in all 5 tests measuring oxidation, not any one of them is really measuring exactly the same property outcome or even its performance. So as I say here, it's very possible that you can have one of these not correlating with the rest of them, or none of them correlating with each other. That can happen. I mean, MPC and UC are the closest that should correlate, that a higher MPC should equate to a higher UC. But the rest of the tests, you may not notice as much shift or difference as you might expect. And even if you do see a trend do something like a sudden reversal, so as an example, an MPC or UC climbing, and then suddenly stabilizing or dropping off, you wouldn't see a shift in the direction that, say, RPVOT, ruler, or acid number would go in. So understand each one of these tests exists for its own reason, and though they're commonly placed together and commonly said to have a bearing on the same data, they don't correlate very well. So as a quick side note, again, not to give you more useless trivia, but to show you some slides I presented a few years back, I did a very similar presentation whereby I showed this shortcoming to these 5 tests. And essentially the burning question at the time was, how do I know if I've got varnish? So I wrote a presentation called Varnish, Is There a Definitive Test? And I went through what I just showed you here in terms of none of those tests really give you an accurate idea if you've actually got varnish, though they can hint at it, but you still don't really know. So then the question is, well then, what is the right test? If it's not one of these 5, is there another test I should be considering? And take this all with a bit of tongue-in-cheek, but here's the test. So it's the oil test, as you pronounce that particular word. It's developed by Dr. Joksung, so hopefully you see where I'm going with this. But it is a fairly simple test. You don't have to do chemical analysis. It's just a visual inspection, so we don't need a lot of tools. We don't need a lot of training, and we can even do this while it's running. So lots of good things about this test. So the basic principle, OIL is an acronym, and it stands for Open Your Equipment and look. I know it seems simple, but ultimately, if you start seeing this, you've got varnish. Doesn't matter what your oil analysis results tell you. Downside to something like this, of course, is, as I'm joking here, it's about as effective as predicting a flat tire, right? You don't know you have a flat tire until you have a flat tire. So it doesn't seem like a very good test. The confirmation only becomes evident once the incident has occurred. So I know it seems like a bit of a joke, and I do digress here, but seriously, if you do a physical inspection, you will have a reasonable idea if you actually got varnish within your system. So I encourage people to open up their reservoirs, look for that bathtub ring that you will see. You can do something as simple as a dipstick. You can even create your own dipstick and have something that's fixed at a certain height within the reservoir. So part of it is above the fluid level, part of it is below the fluid level, and it's just easy to remove like a dipstick that you can pull out, because where varnish deposits typically will occur is in areas where the oil temperature drops, so they cool. It's kind of like water condensing, or tight clearances. So if you pull filters or suction strainers or anything like that, always do a visual inspection on those, because that will be where you might see varnish, insolubles collecting and turning into varnish. So just a quick little side venture here in terms of the discussion about those oxidation tests. Now, moving on to the last part of the presentation, I said we talk about ferrous wear and analytical ferrography. So with ferrous wear, it's a fairly simple test. You take a test tube full of oil, you stick it inside of a magnetic flux, and it compares it to the reference magnetic flux in the instrument, and will tell you how much ferromagnetic material is in the sample. It is a very quick and dirty. It does report it as a gravimetric, as a ppm by weight. But you have no idea, what the particle size distribution is, what wear mechanisms causing them to be there. You just know overall how much you have. So the limitations are, well, the good one is it's not limited on particle size, but that also means that, of course, it might not correlate with your elemental spectrometry or particle counting. As for interferences, though you think ferromagnetic always refers to iron, there are other metals like cobalt and chromium that can be ferromagnetic. Cobalt's not that common, but chromium is used in a lot of coatings and is used in some alloys. So understand that there is some skewing for that. It's not usually that significant, but it's measuring more than just iron. Now, on the flip side, we have analytical ferrography, which is a much more intensive test and can begin one of two ways. The common way that we think of when we picture analytical ferrography beginning is by creating a ferrogram, which is what you see pictured off to the right here. It is a glass slide on an incline. At the top of the picture, that would be the top of the incline, and the bottom of the picture would be the low point, the bottom of the incline. What we do is we flow oil down the incline, and the particles will settle out from largest to smallest just based on fluid dynamics. Now, I know you're looking at that picture saying, well, yeah, but they wouldn't sort out into cute little smooth lines. They don't. That is aided by a series of magnets that are placed underneath the slope. So magnetic particles will align, and non-magnetic particles will randomly distribute themselves across the ferrogram. But like I said, due to fluid dynamics, they will sort from largest to smallest. So we can start the test by creating a ferrogram, or we can start the test by creating a patch. Now with a patch, again, we just use a membrane filter. We filter a certain volume of oil through the patch, we rinse away all the oil, and we're left with only the particulate that was able to be trapped on the patch. So in this case, we have no magnets helping align particles, and we have no sorting of particles. It's just random distribution everywhere. Now with either of these two beginnings, the next step we do is do fairly in-depth microscopic analysis. Now the limitation to the microscopic analysis is we're not limited to particle size. So again, we should appreciate it won't correlate with other tests. But with this test, we're not doing a quantitative measurement. We're not measuring in parts per million or any variation like that. We basically just categorize it into trace, low, moderate, and severe. So it's just ballpark concentrations. And the emphasis is instead of how much, it's more the what is it. And the what is it is identified by morphology. We actually look at particle shapes and we look at particle sizes to help determine what kind of mechanism caused the particle to be there, and based on its size, how severe might it be. So it doesn't have any significant interferences, so that's pretty good. And the categories of measurement as defined by ASTM are as follows. So the first two, rubbing wear and rolling contact fatigue, are generally considered to be from normal wear mechanisms. So as long as the particles observed following these definitions remain small, generally speaking, you can consider your analytical photography to be in the realm of normal, even if the concentration is higher, like severe or moderate. But once we get into the other types, the cutting wear, as you see here, or chunks, spheres, and some of the other ones I'm going to quickly show you, once we start seeing these things present in the oil, regardless of the overall level and regardless of the size, they are thought to be from abnormal wear modes or contamination. So what we then interpret is the actual levels and sizes to see just exactly how severe it is. Now, chunks, I know, doesn't sound terribly scientific, but basically it's a way of categorizing metal particles that are larger than 5 microns that didn't essentially fit the first three categories. Spheres, you can see there what causes them. There's also 3 other categories relating to some different types of wear modes. So there's corrosion. Dark metallic oxides is essentially welding wear when you have 2 surfaces under such extreme pressure and contact that they temporarily weld to each other and then pull away. And red oxides is a fancy way of saying rust particles. The last 2 categories as defined by ASTM deal with contamination. So we've got a specific category for dust and dirt, and then we've got a catch-all category for other. Now at Test Oil, we include a 3rd bonus category that we call oxidation byproducts to help separate out any of those that may appear on the patch, instead of just burying that particular result with the other. Now, our little summary so far here is that understand that ferrous wear and analytical photography, as I'm saying here, have less in common than Crackle and Carl Fisher. Because ferrous wear is kind of like a Crackle test, right? It's a very quick and dirty test. Analytical photography is actually even more than just a Carl Fisher. Carl Fisher is a quantitative way of measuring water content. But analytical photography does attempt to not just quantify what's there, but also qualify what wear mechanism caused it to be there and the size of the particles. So there is a greater discrepancy between these 2 tests than there is between those 2 water tests. The other thing to note, though, is that neither test has a particle size limitation, so we should appreciate that these 2 tests will not correlate with elemental spectrometry or particle counting. But as I said earlier, the correlation or lack of correlation can still tell you something. So when we see, as an example, picking on elemental spectrometry and ferrous wear concentration as just 2 quick, simple tests, if elemental spectrometry is high, but ferrous wear is low, then again, I'm going to say most of the wear particles that we're seeing are from normal wear mechanisms. If both are high, I would say we're transitioning from normal to severe. And if elemental spectrometry was low, but it was the ferrous wear that was high, I would think then that most of the wear particles we're seeing are from more severe modes. So that gives you an idea, how you can interpret and understand what you are seeing or not seeing on the report, and make sure that you're interpreting the data as best as possible. So as an overall summary, what I've been trying to convey as a message here is the key to overcoming limitations is first, pick the test that will give you the data that will tell you what you're hoping to find out. Right? If you do not select the right test, and just because you select a test in the right category still doesn't necessarily mean you're going to get the right data. You have to know which test in which category is going to provide you something useful, meaningful. That is sort of step number 1. When you do the interpretation now, if you know that the data only goes so far, you have to then understand, is there a follow-up test that I could do? Even, like I said, if it only eliminates a possibility, right? You might not find the perfect test that absolutely confirms something is occurring, but you can find an additional test to eliminate that some other issue is occurring. So as a quick example on that one, if you see MPC results that are constantly increasing, which makes you think that there's varnish. Like I said, there's no real test that tells you if you've got varnish. But if you see a sudden decrease in your MPC values and now you're suspecting that there is varnish in your system, having the inability to pick a test that would confirm the varnish, you could go to alternate testing to confirm that, in fact, this result makes some sense, that the decrease is real. So what you could do is you could do, say, an ultracentrifuge to confirm that the results on it are also low, or you could do a check on your particle count or whatnot, whether it be pore block or optical, to see if the particle count did a sudden decrease, because then you're confirming that there is less material in the oil sample. So, last but not least, if there is ever a deviation in trend that indicates something abnormal may be happening, so you have to ask yourself, did that sudden shift in the trend occur because I exceeded the limitation of the test? Should I request an additional test, or is there other data I can look at? It's always the important side of reading the whole report and not just focusing on a single test or single measurement. Now, to wrap up this whole presentation, I did begin by saying the first limitation is test selection. Of course, that would hint at that there's a second limitation. The second limitation is test accuracy. So if you really want to get good at interpreting oil analysis results, something that you should become slightly familiar with, you do not have to memorize nor have as a handy-dandy reference available at all times, but you should know just how accurate any one test method is. There are many times that people will overinterpret data because they will see small changes in the data and assume that that's indicating something that's really happening. Whereas those of us who are experienced with the analytical side of this type of testing can appreciate that there's error within the method, there's noise on the instrument, and that some of these small changes are just actually expected within normal data. So as you get more and more well-versed with oil analysis, you'll start to appreciate these. Like I said, you don't have to look them up or know them off by heart, but many a test has at least a 10%, if not higher, variation, even measuring the exact same sample twice in a row. So when you have two samples separated by a month or 3 months worth of service, do expect there will be some shifts in the data that may be simply because of the testing and not just because of actual changes within the lubrication system or degradation of the lubricant itself. So with that, I will pause now, turn it back over to Taylor, and see if there's been any questions that have been posted. If you don't ask a question now, by all means, you can always email me later. So I put my email up on screen there, but we'll take a look and see if anyone's used the chat. So Taylor, how are we doing?
All right, thank you so much, Evan. Looks like we do have a few questions. Okay, the first one here, what test do you recommend if the elemental is low and the particle count is high?
One of the easy answers to that would be to follow through with something like analytical ferrography. Because if I've got a high particle count, I'm dealing with larger particles, and these would be visible through analytical ferrography, and that would confirm to me, are they in fact just contaminants or are they wear metals? So that would be sort of what I would like to see. Simpler than that, though, you could just get away with a simple patch. You could do a visual on a patch, and that would provide you a much coarser, more qualitative answer, but depending on how much you're willing to spend and how far you're willing to take it. But that's sort of the go-to answer. A secondary answer that you could do is you could go to what we call EDXRF, energy dispersive X-ray fluorescence. It is an alternate method of elemental spectrometry, so it is still elemental, it's still spectrometry, but rather than the way I described, it's done using X-rays, and that particular technology is not size limited, so it could measure all types of particles, but again, it would only give you the elements, not compounds, alloys, or anything like that. So I would favor analytical ferrography, but it depends on what you suspect it is, or like I said, how much money you're willing to spend. There you go.
All right, and it looks like there are a couple more questions, but I think that they would be best answered through email. I would like to thank everyone for joining us today, and thank you so much, Evan, for presenting.
Right. Thank you, Taylor.